Welcome you all to the second session of our FIWARE Data Spaces onboarding series. I will talk today about decentralized identity and access management, especially in FIWARE Data Spaces. My name is Stefan Wiedemann. I'm Senior Software Engineer at FICodes, and I'm working on FIWARE Data Spaces essentially since we started to work on data spaces in FIWARE. Okay, let me give you a short overview about what I will talk about today. I will start with a short introduction on why we need decentralized IAM in a data space. Then I will give you a short introduction into decentralized identity itself. I will also talk in detail there about verifiable credentials and about decentralized identifiers. In the third section, we will talk about authentication, authorization in a FIWARE data space. And the fourth part of the session will be about policy enforcement with ODRL. Okay, then without further delay, let's get into the actual presentation. So since this is part of the data spaces onboarding series, the obvious question is, why do we need to talk about decentralized identity and access management? To remind you a little about how a data space conceptually looks like, it usually consists of different participants that can take various roles. In a FIWARE data space, you will have usually a number of data providers. I pictured them here in green. We have a couple of data consumers. We also might have one or multiple marketplaces. Those consumers not necessarily have the same role, have only one role. They can also take multiple roles. So a data provider also can be a consumer at the same time. But for better understanding, it's easier to look at them in their roles, because when they act, they usually will take one of those roles. Beside the participants itself, the participants are usually organizations, and those organizations are not just a participant of the data space. They also have technical and human actors that will act on behalf of those participants. So you might have, so your data provider will usually have services that they are offered to the other consumers in the data space. The data consumers can have employees or customers that use the services of a data provider. They also can have services that use data for further processing of a data provider. So maybe a machine will act on their behalf, and all of those will connect to each other. In our data space, usually the participants don't have any connection between each other besides actually being part of the data space. And beside that, they also don't have any knowledge about each other's actors. So my data provider A doesn't know how many employees our consumer A has, or it does also not know how many services that wants to access data the consumer B has, or even if they have customers, or how many of them. Usually, they also shouldn't know about that, because this could leak potentially business data. It could become a problem in terms of GDPR. So in general, our participants don't really need to know anything about each other, and they don't have any connection to each other. But that obviously brings also a couple of problems with itself. Because when the participants then talk to each other, for example, when a consumer tries to access the service of a provider, how does the provider identify those actors? So how does data provider C know that the actor actually belongs to the consumer A, or is even a part of the data space? And how could it authorize the actions of this actor? Because the actors itself could have different permissions inside for one of the participants. The provider might give different powers to actors of various participants. So it might allow a participant of consumer A to read some data, while consumer B is not allowed to do this because it didn't buy access to that. Or how does the marketplace know that an actor of the consumer is actually allowed to buy an offer that is part of the data space? And beside that, how do they connect the actual consumers or the actual actors to their organizations as part of the data space? Another problem is how is a new participant how can a new participant join to a data space? A data space usually is not a static construct where it's not allowed to add new members over the lifetime. But if a new participant joins a data space, it also requires a new trust relationship between the participants and all other participants in the data space. And probably even more frequent event is when a new actor joins one of the participants. This participant then needs to be recognized by all participants in the data space, because if not, the consumer might not be able to, the actor might not be able to act on behalf of the participant when accessing data from others. Um, so one might say we have already a lot of technical solutions to log into such systems. The most obvious is just use a central login facility where everyone is registered, can log in and then access the data or the services of each other. That might be easy to use, and it's also easy to use for the users and consumers, but it also puts all power on a single entity. We have a very powerful data sync of essentially everyone that is registered inside a data space and that also knows essentially everything that happens in a data space. And it works a lot against the decentral nature of a data space. I assume that Juanjo did already explain a little about this decentralized nature of data spaces last week. So one of the features is actually decentralization. And if we now build a central login, we are working against one of the base principles of a data space. Now we can ease this a little by federating identity, which is something we are all very much used to. So everybody knows going to a website and then choosing to log in with its Google, GitHub, or Facebook account or whatever. That might put less reliance on a central IDP, but we still rely on, in this case, multiple central providers. And if we just increase the number of those providers, this might decrease decentralization, but it also increases the number of the complexity, while it doesn't really take away the fundamental problem. So in my opinion, the logical conclusion is if we have a decentralized system, we also have to talk about decentralized identity. That's why I now will start with a real introduction into what decentralized identity is. Decentralized identity essentially, or the idea of decentralized identity is essentially copied from the physical world. The idea is to really copy what we already did there and augment it with digital powers. Every one of us has a wallet which contains a number of cards that contain essentially our whole identity, or let's say parts of our identity. And we are able to present this identity to everyone that we are deciding to present it. We don't need to ask somebody to show our national ID card, for example, or to present a membership card to anyone. So the cards in our wallet are already some kind of decentralized identity. And the idea of decentralized identity in a digital system is now to take this and essentially rebuild it in the digital environment. If we think about this, as I already mentioned, we all have those cards in the wallet. So the identity of a natural person would be combined essentially of stuff like the national ID card, driver's license, an employee badge that you use to authenticate yourself when you go into the office, maybe club membership cards when you go to your fitness club or whatever, maybe a diploma or proof of residence. All of these are things that we already carry around with us. And now we have the idea of transporting this into the digital world. Beside natural persons, obviously in the data space, we also need to think about legal persons. But a legal person essentially is constructed very similar if you think about it. Our legal person will have some business registry ID. Most of them will have a legal entity identifier. A business or a legal person also often carries a number of ISO certificates certifying some of their capabilities or compliance with certain regulations. A legal person usually has a bank solvency, they have tax compliance and tax IDs, and they might also have some certification about their GDPR compliance. All of these are things that can be combined or are part of the identity of our legal person. Okay, now that we have the identity of our legal person, in the real world, we can also have a look how authentication works in the real world. Um, so our plastic card, the national ID. If we think about how authentication works with that, we will have a better, or let's say easier way to understand how this will also work in the digital world in the next step. We usually have a government that, in terms of most of us, is registered in the European Union, and it's the one that issues our national ID cards to to the citizens of this government of this country. Um, the ID card that is issued follows some schemas and standards that are commonly agreed on and defined by the European Union, so that everybody will understand this ID card. And once it's issued, our natural persons, so we as the citizens of the country, can use this national ID card to authenticate ourselves and to essentially everyone. For example, if I go to the airport and want to come back to, in my case, Germany, I can present my national ID card to some police officer, and it then can verify this card. It will check some authenticity features on this card, and it will also check that it's actually a national ID card, as it is defined first by the European Union, but also by the German government in this case. Depending on the result of this verification, I'm allowed to come back in or not. And if we take a look, we can essentially build exactly the same in the digital world. So how will this work with verifiable credentials, which is our, let's say, digital equivalent to the national ID card? We also have somebody that actually is registered at a verifiable data registry. As you remember before, it was the European Union. This verifiable data registry could be something that a database did agree on. It could also be multiple verifiable data registries that are used depending on the purpose. The issuer will then issue this credential, which could be a national ID card. There also exists in digital form in some cases. It will issue the credential to our holder. Our holder has now its verifiable credential, and it will usually also store it in something that we call wallet, very similar to what we do in the real world, and can use it to present it to essentially everyone that wants to that asks for authentication, and can then verify this. So we have the verifier here that will ask for authentication. So our person can send its verifiable credential, in this case as a presentation. I will come to the details of that later. And the verifier then can verify this credential. Also, again, very similar to it happens in the real world, because also our verifiable credential has some authenticity features, most notably the signature on the credential, which could easily be verified by the verifier. Then it could also check that it uses a known schema and that the issuer is also registered in the verifiable data registry, and it can decide to actually accept that credential once all the verification is done. Yeah, that's essentially how we could transport this real-world authentication process into the digital world. Now, let's get further into the details. Let's start with what actually a verifiable credential is, because that is, as you can imagine after my after the last slide, very fundamental to the whole idea of digital identity and decentralized IAM. A verifiable credential is a tamper-proof, digitally signed document that securely proves claims about an individual or entity, allowing verification without directly involving the issuer. That already gives us an idea about why it might be interesting to be used in a decentralized identity environment like the data space, because it could be used independently from whomever did issue it. A verifiable credential, as we use it, is essentially a document that can contain any kind of data, mostly data that is representable in a JSON format. And this data is combined with digital signatures so that it becomes tamper-proof and can be verified. Um, there is already a specification by the W3C about the verifiable credentials. I linked the data model 2.0 here, which is currently still a draft version. The FIWARE Database Connector mostly is compliant with data model 1.1, but we're also working on becoming compliant with data model 2.0. Which probably is the future of verifiable credentials in most environments. The data model defines essentially a basic document structure and the features that each of those verifiable credentials needs to fulfill so that they can be exchanged and verified in a standardized way by verifiers, issuers, and holders. And as mentioned, this standard is already somewhat widely adopted by various regulation and standardization bodies. For example, as part of the European Digital Identity Wallet Reference Architecture, or by the OpenID Foundation as the set of OpenID for verifiable credentials standards. I mentioned especially the second one because the FIWARE Database Connector relies very heavily on the standards provided by this OpenID for verifiable credentials standard package or flow package. Yeah, so I think it's important to mention this here. Okay, but now how does an actual verifiable credential look like? I used the JSON representation of the credential here. I will explain later that there are various formats to actually encode a verifiable credential. But in the end, all of them can be more or less decoded to a JSON document. And I think it's the most readable version. So I will go through its features on the JSON on the JSON representation. A verifiable credential is essentially combined of three building blocks. We have the credential metadata, we have some claims, and we have some proofs. The metadata tells us something about the credential itself and how it can be used and verified. The claims are the part that we will use to, that we actually have the data, the payload in, and the proofs is what we can use to do the actual verification. The proof is important to have our credential tamper-proof, allows us to trust in the contents of a credential. The example I used here is a somewhat minified version of a national ID card, as it's currently discussed. As far as I know, there is no common standard yet in Europe, but it will look something like this with obviously much more properties. And now let's take a deeper look of the components of this verifiable credential. Let's start with the metadata. As mentioned, the metadata provides the contextual and technical information about the credential itself. It will help the verifier so that it can understand if this is a valid credential, and it will provide the provenance and usage context of the credential. So what is this credential intended to be used for, and how can I understand it and validate it? We have a number of required properties on the metadata in every credential. And there are also some optional that makes the usage in various use cases much easier. Let's start with the required one. Every credential will have an add context property. This provides the context for interpreting the data within the credential, and it's often used to link to standards and schemas that the verifier then can use to better understand the contents of the credential. The second required property is the type of the credential. This will also help the verifier to interpret the purpose of the credential and understand its contents. And we have the third one, which is very important to build the trust, especially in our data spaces, because it's the issuer. This field, we can see it here, contains the information about the entity that actually created and issued the credential to our now credential holder. This issuer information can be used to verify the document, and it essentially tells the verifier, or it essentially means that we have to trust this issuer if we want to trust the contents of our verifiable credential. So it is a very important field. Then we have a couple of optional metadata fields, like the IDs, the names, descriptions, that can be used for various purposes. The ID, for example, is often used as part of some revocation lists. So it uniquely identifies the verifiable credential. And if you want the power to actually invalidate a credential after it was created, we have to build some revocation lists that the verifier can look up. Because, as already mentioned, the whole idea is that this credential can be used independently from anyone else, which also means that no external service usually is contacted for the verification, so it's not so easy to actually invalidate it. There's the concept of revocation lists, and IDs can be used for this. The credential status field can be seen very similar, because it could provide information on the service information on the credential, where a verifier can look up if this can look up the current status of this credential. Like, for example, was it revoked? We have fields like names and descriptions, which is usually used by wallets to make the, let's say, presentation of the credential in a user wallet and the recognize and the user experience of the holder easier. And then we also often have the valid from and valid until fields in our credential, which defines when this credential is actually valid. So it allows us to tell that this national ID card is only valid until 2034, very similar to our national ID cards. At least mine also has, I think, an experience period of 10 years. We can do the same for verifiable credentials. Depending on the use case, this could also be much smaller or longer. That's very flexible. The next block after the metadata is the claims. As mentioned, the claims section is where the actual information is stored, where we also can find the assertions that the issuer makes about our about the subject of our credential. The claims are stored in a property called credential subject that can contain a set of objects. It could be also a single object with the specific attributes or data pieces that the issuer attests about the subject. So in our example, the issuer, our government agency, attests the name and the date of birth, nationality, and the address of our example of our user here. The claims usually should follow a specified data schema, so that every verifier can actually use it and understand it. We cannot just replace the names, because then the verifier or whomever receives the credential doesn't know where to look for a given value. Then the subject also often contains a field called ID. That's not mandatory. So actually in the credential subject, there are no mandatory fields. But one very commonly used is the ID of the credential subject. This ID often links the claims to a specific holder of the credential, which could be, for example, help a verifier to confirm that the claim truly applies to the presenting subject. What does it mean? You can again compare this to how a national ID card works in the real world, because as part of the information on our ID card, you usually have a photo, and this photo can then be used to compare if the information in the national ID card actually belongs to the one that presents it, by just comparing the photo with the actual person. And we can do this here by comparing the ID of the credential subject with the ID of the holder of the credential that actually presents it to us. So a verifier has or can have the mechanisms to verify that it gets a credential only from the one that it belongs to. And then the third section of a verified credential is the proof section. The proof contains the actual details about the digital signature on the credential. The digital signature should ensure that our credential wasn't tampered and that we can check that it actually comes from the one that is inserted there as an issuer. Let's go through the details of the proof itself. The proof always has a property called type. The proof type, it contains the type of the proof that we have. This type also determines what other fields are required to secure and verify the proof itself, because that depends on actually on how the proof was created, and we need this information to actually check the signature. Typically, it also contains a proof purpose. So what should this proof be used for verifiable credential? That's often for assertion, but there could be other proof purposes, and they are usually they should ensure that the issuer wasn't more or less tricked into signing a credential that is then used for purposes that it wasn't intended for. The verification method is often used in combination with the issuer ID itself, because it will provide the information that is required to verify the proof itself. In this example here, it would, for example, reference a specific key as part of our issuer's identity. I come to decentralized identity later, so it would make more sense. You will better understand this after the next section. And then we have the JWS section, which, at least for the type ED signature that we have here, contains the actual digital signature of our credential, which then ensures that the credential has not been tampered with. So if we verify credential, the first step usually is we evaluate the proof and check the signature. And if the signature is broken, we don't have to do any additional verification, because we cannot trust the credential itself at all anymore. So beside verifiable credentials, another term that is very important is the verifiable presentation. I used the term presentation already in the description of the digital authentication before, because a holder usually shows the verifiable credential in form of a verifiable presentation to a verifier. So it presents its identity to the verifier. A verifiable presentation therefore looks very similar to a verifiable credential, just as the type verifiable presentation. And it can contain one or more verifiable credentials created by a holder, so that it can share information with the verifier. It's very good that it can combine multiple credentials, because a verifier might require multiple credentials to get all the attributes that it needs for authentication. Again, an example from the real world would be if you drive around and get police will stop you, then you usually have to present your driver's license and the license of ownership of your car. So it's not one credential that you then have to present, but two. And there are various use cases that you can, in the digital world, where you also might need multiple credentials to present your identity. The verifiable presentation itself also contains a proof that ensures the integrity of the presentation itself. Why is this important? Obviously, because the presentation could essentially be altered by someone during the presentation. But if it's signed by a holder itself, the verifier can check that it actually comes from the one it's expected from. And it also enables the verifier to check the contents of the credential. I mentioned the ID of the credential subject before, and to have mechanisms to actually check that the holder is the one that referenced in the subject. And now the verifier can check the verifiable presentation, the proof on the verifiable presentation, and see that this was actually presented by the one that is mentioned as the credential subject. So if the national ID card is presented, it can check that it was presented actually in this case by our Maria Mustafa with this personal identifier. So yeah, I already told that I only use the JSON format to present the verifiable credentials because it makes them more readable. But there are current various types of verifiable credentials specified and used. I just took out 4 that are quite common and that you will probably find a lot when it's about the FIWARE data spaces. The currently most important in FIWARE data space is the JWT-VC credential. It represents a verifiable credential essentially as a JSON web token. So you will see the credential that we have as part of the payload of the credential, as part of the JWT token, and in the header you will find information about the issuer and also the keys to be used, and you will have the typical signature section that every JWT token has. This format leverages on established standards that we all know and that are easy to implement, and where we can reuse a lot of tools that we already have, and the credential can be easily validated by a verifier. A very interesting extension to the JWT VC format is the VC plus SD JWT. SD stands for Selective Disclosure, which is an extension to the JWT standard, which is also already specified. That enables the privacy preserving way of presenting verifiable credentials. In this case, a holder can decide what parts of a credential it wants to present to an actual verifier. If you, for example, imagine somebody is trying to access an adults only service that needs to present a proof of its age. This usually happens by presenting a national ID card, for example, again. But the service usually only doesn't need to know about the age of the person, not the name, the address, and so on. And with the normal verifiable credential, you would have to present all the information and just trust into the verifier that it doesn't store anything it shouldn't and doesn't do anything with it that it shouldn't. While with the verifiable credential plus SD JWT, you can clearly define what parts of the credential should be visible to the verifier, while the signature on the credential still keeps intact. So you can present your national ID card with only the age chapter readable, but not the name, not the address, and so on. That's why I think this VCSD JWT is quite an interesting format to be used for credentials. Then there is the linked data proof credential, which was quite famous, I would say, 2 years ago. And it was also the one that we started with at the FIWARE Data Space Connector. But it already has, I would say, lost a lot to the JWT-VC credential. So it's just mentioned here in case somebody stumbles above it. And then there is another one which is quite interesting, which is the MDL, which is a specialized structure for representing mobile driver's licenses. We don't use it in our FIWARE framework, but since it's already an ISO standard and used in various environments, I think it's a nice example of the actual usage of verifiable credentials. Now that we have verifiable credentials, we need to come to the decentralized identifiers. Because especially for our use case, verifiable credentials make most sense in combination with decentralized identifiers. So first again, what is a decentralized identifier? A decentralized identifier is a new type of identifier that enables verifiable self-sovereign digital identities without relying on the central authority, allowing an individual to control their own identities and associated data securely and independently. Again, we have already a couple of buzzwords that very much sound like decentralized identity and like something that we want to have in our data space. The identity can be controlled independently from, let's say, third-party service. That's something that we need. It allows someone to present its data securely and control its data, and all of this without relying on a central authority. That's something we want in our data space because we don't want the central login facility, as we mentioned. That's why decentralized identifiers is the second important concept to be understood before we go to our identity and access management actually implemented. Decentralized identifiers are also already specified by the W3C, so it's also, I would say, well-established standard. W3C defines the syntax for an identifier um, for those identifiers, and the decentralized identifiers control allows the controller of an identity to actually prove the control about this identity without requiring permission from anyone else. Um, this is also something that we want, which is again very similar to our real-world examples with the cards that I can present to anyone without asking for permission because I have it in my hand, and I can do the same with the decentralized identity. The DID itself, from a technical perspective, is more or less an URI associated with a document that allows us trustable interaction. So this document connected to the DID contains cryptographic material, verification methods, or services to prove the control about the identity. This is still quite abstract, so go into some specific example. How does a decentralized identifier look like? It's clearly defined how a decentralized identifier is built. It always starts with the DID prefix. This prefix indicates that the given URI is a decentralized identifier. After the prefix, we will find the method name. There are various different methods to be used for decentralized identifiers, and the method name references the specific DID method that our DID uses here. The method itself specifies how the method-specific ID is generated. This is the ID that we will find as the third part of our decentralized identifier. It specifies how the associated DID document is created. It also specifies how the DID can be used to resolve this DID document, and it defines how the DID document can be used to verify authenticity. So when I get a DID and I resolve the method and the ID, I have a clear way of verifying the authenticity of essentially any data that the holder of this ID presents to me. And we have a fourth part of the credential, a fourth optional part of our decentralized identifier, which is the additional components section, which usually references some part of the DID document or an external resource. The concrete meaning of the additional component again depends on the concrete method specified by the method name. In the FIWARE database connector, we currently support three methods: didKey, didWeb, and didLC. didLC is still in work, so it's not fully supported yet, but this is something that we're working on and that will definitely come. I have some examples for each of the various decentralized identifiers here. The first one is a didKey, then we have didWeb and didLC. The didKey is, in this case, more or less a random holder of a credential. The second didWeb one is actually the ID that we created for a demo implementation in one of the FIWARE projects. And this didLC is actually didLC from the FIWARE Foundation. So this could be referenced to the FIWARE Foundation. Now let's have a closer look into those three methods, because we need to somewhat understand them to understand how all of this works in a FIWARE environment. Let's take this didKey. The didKey itself is a method that uses the public key of the key material from our holder as part of its identifier, and therefore directly incorporating the cryptographic keys into the DID. This makes our DID really safe contained, so you don't need any additional service to find out about the public key of our holder and verify data that you get from the holder. The direct key mapping allows straightforward verification of ownership, essentially because the key is already integrated. It's easy to create because you can more or less generate it with standard key creation mechanisms that are well established. And in the FIWARE database connector, more or less is an ideal. It's ideal to be used for the identification of individuals or services, so basically the holders. We will see later that for organizations there might be better fits, but DID-key is a very good idea to be used for holders of credentials like the employees, for example. How does the coding of this ID work? The ID itself is base 58 PTC encoded key, and we have a prefix to this, which is the multi-codec identifier of the key date. That sounds more complicated than it is, so we essentially can look into a table what this ZDN prefix means. In our case, it indicates that it's a P256 key, and then we can just decode the key part and use it for verification. The web looks, in my opinion, a little bit nicer, but it also already reveals something about our holder of the key, our identity. Essentially, that we have the URL that our key material is available on. The method is designed to be used in web environments and provides a way to create the identifiers that are resolvable with the standard mechanisms of the web. The DID document is served at a well-known path that can be derived from the key itself. And in the FIWARE database connector, we mostly use it for the participating organizations. So an organization most of the time already has certificates and most of the time already has some endpoints in the web. And they just can provide also the DID JSON document and therefore can easily create a DID web to be used for their identity. How does the coding work? Following the method definition, we can just put the HTTPS prefix to our ID. HTTPS is enforced by the method, which should ensure the security of the DID document. So this cannot be just an HTTP path. And then we also know from the method specification that the additional argument should be used as a subpath to this address, and then it should be appended with the JSON, where we can find our actual JSON document. When I click here, you can see this is actually a valid JSON document. It contains various information about verification methods, key material associated with this DID, and this could now be used to actually verify credentials or any data under control of this identifier. The third important method that we have is DID-LC. That's a quite interesting one because it bridges our decentralized identifiers into an already existing regulated world. DID-LC is a method for legal persons that uses the IDAS regulation. It is built by the identifier is building from the IDAS certificate that is already issued to various legal persons. It supports different kinds of IDs that are used in those IDAS certificates. For example, the VIT number, which would be a national tax identifier, which we have here in our example. It's the tax identifier. We have the legal entity identifiers could be used. We have also something like a trade register. All of this essentially reuses existing infrastructure and brings that into the world of the decentralized identifiers. IDAS regulation already specifies the certificates that we have, and then we can use this to verify credentials following the charter specification, which is based on JSON on JWS again. And yeah, according to the specification, the certificate material is always already included in the Jose header of credential. This is why we have a little, let's say, special case of DID-LC here, because I cannot use DID-LC to directly get access to the certificate. I just know how to verify the data when I receive it. So if I get a JWT credential from somebody using the identifier DID-LC, I know that I have to look into the headers of the credential and can find the certificate material there. This method is already used in the DOME Marketplace project, which is a marketplace for the European Union, digital marketplace for the European Union, and is also further developed as part of this project. So Now that we have the, I would say, theoretical fundament of the digital identity and um, verifiable credentials. Now let's look how decentralized identity and access management works in a FIWARE data space. Um, we are back to the initial picture of our data space with all the participants, and now instead of a central login, we will have something called the verifiable data registry, where all participants essentially put trust in. This verifiable data registry doesn't need to be a central point. It could also be various global trusted lists or a single clustered list. Um, this is something that is very much open to the data space and what you want to achieve with it. It doesn't even need to be part directly of the data space. A trusted list can also be provided by some external services. So for a national ID card, as we have, the trusted list is probably something provided by a government. It could also be something like a third party, that's called third party trust framework like GaiaX, um, where you can integrate into their trust framework and use it as the trust anchor for your data space. I will not go into more details about GaiaX here, but we will have this in session 6 of our webinar series and have a closer look on how to integrate that. We also support additional trusted lists that can then be used for defining more fine-grained access for the individual participants. But going to the actual architecture of the FIWARE data space connector and let's say making this more practical, I will go now step by step through the whole process of issuing a credential and using it for authentication authorization in a FIWARE data space connector, so that you hopefully then better understand what I talk about here. The first step that I will talk about is the actual issuance of the credential. Because if I'm a consumer organization and I'm registered in my data space, I need to somewhat issue credentials to my actors. Those actors can be, as we already talked about, user or machine service, machine essentially. We use the user here because that makes it a little more visible. The only difference is essentially in this step where we don't have a browser involved, but doing this with an application itself. But the whole flow itself is the same, so it doesn't really make a difference. But we start with issuing a verifiable credential to our user. Issuance in our data spaces follows the OpenID for verifiable credentials issuance standard. This is defined by the OpenID Foundation, as I already mentioned, and clearly defines how a wallet can receive a credential from an issuer. In our environments or in our FIWARE data space connector, we usually use Keycloak as an issuer. As some of you might know, Keycloak since version 25 supports verifiable credentials issuance as an experimental feature. We were able to contribute this to the upstream, and it's still continuously developed. So I think that's a very good solution for us because we can rely on a stable component here. And the credential itself will then be stored in the wallet of our actor, in this case, the user, so that it can be used to interact with other participants in our environment. It can use then the credential to actually authenticate at them. So from a consuming organization, everything that is more or less required to participate in a FIWARE data space is an issuer and a way and essentially an actor that can store the credential in the wallet. Consumer organizations, therefore, quite easy to build. But now look how this looks on the provider side and how we can interact with the provider. Because what now starts is our user wants to actually use its browser to access a service from our data provider. So we might have a data portal and the, let's say, data analyst of our consumer wants to access data, a data set. Therefore, the user tries to access this website and gets to the protected resource. That's something we all know. So you will get to a login page and you will need to log in. In our case, that won't be a password and something, a password and a username, but you will be redirected to something that we call off portal here, but it's essentially kind of a part of the verifier which can be embedded in any front end. And it can present you a QR code. This QR code can then be used by the wallet and can be scanned by the wallet. And it contains the information that the wallet needs to connect the actual verifier with, because the wallet is not directly connected to the browser often. It could, for example, be the mobile phone of the user. There are also enterprise solutions that might be integrated with the browser, but usually it's not the same device that is actually using the service. So we need a way to tell the wallet where it should present the credentials itself. This happens through the QR code. This QR code now contains the address of the verifier. It will also contain some additional information about the service to be requested, like the service ID or the scope of the request. With this information, the wallet actually goes to the verifier and asks for starting the presentation process through the OpenID for verifiable presentation flow. This is again specified by the OpenID Foundation and defines how a credential should be exchanged between a wallet and the verifier. The verifier, which is an implementation from the FIWARE Foundation here, requests the credentials configuration from the so-called credentials config service. Why do we do this? This allows us to very fine-grained define which credentials should be requested from the wallet for a given service. And it also defines which trusted lists we should use for those credentials in the context of a service. Let's go to an example about this, because this might be confusing on first glance. So we have the credentials config service as mentioned. It provides a REST API where you can exactly specify the credentials that a service requires to be used for. We have the ID of our service. This could be the one providing the data set. And we can define the scopes that can be that this service supports. For example, reading the data set and writing this data set. We can define what credentials a read on this service requires. In this case, a user identity credential. And we also can define in what trust lists we should look into. We can define the trusted participants list and also the trusted issues list. The difference between them is something I will explain, I think, in about 5 minutes. And so we can define exactly what we want for a read, and we can also define what we want to request in terms of write. So, for example, in the example of our data set, we might only allow employees to actually write. So we ask for an employee credential, and this employee credential might have to be included in our local issuers list. So we only trust our employees to actually write on this data set. The credentials config service allows us to configure that also dynamically at runtime, so that the verifier can constantly look up the credentials that it should request from the wallet. Now that the wallet knows what it requires, it will request exactly those credentials from the wallet. The wallet then will create a verifiable presentation, as we have seen in the verifiable presentation section, and will present it to the verifier. This contains the credentials that we used, and it's signed with the key of this actual user. Then the verifier essentially starts its work in verifying the signature of the credential itself. It starts with verifying the signature of the presentation itself, and it will then verify the signature of the contained credentials. Because if those signatures are not intact, we essentially can skip every additional check. Once that is done, it will check at the credentials config service if all credentials that we require are included and the trusted list to be used. This does not necessarily happen in secret, so the verifier can cache all those information from before, but from let's say logical from a logical perspective, the verifier now checks the configuration. As the next step, the verifier will check that the issuer of this credential is included in the participants list of our data space. Essentially just checking is the ID that issued that credential part of our data space. This usually is an optional step that can be configured at the credentials config service, but since we talk about data spaces, it's something that is very common, so I listed here as an explicit step. The next step, we will check the credential, the credential itself at all the lists that were configured in the credentials config service, be it local lists or external lists. So, for example, is the issuer of our national ID card registered in the global trust from our government? Or is it included in our local trusted issuers list? The local trusted issuers list gives us some more power to define who's allowed to attest what, and therefore more fine-grained control on the claims. Let's take a look how this will look like. The trusted issuers list is again an implementation from the FIWARE Foundation here. It implements the EPSI Trusted Issuers Registry API. That's a well-defined API for more or less listing trusted issuers and their properties. That's why we decided to reuse it. This component can be used as a participant list, where we only check that it's included, but it can also be used for what we call the trusted issuers list. You will have a fine-grained control about what to trust in a credential. You can configure that the issuer, in this case the ID Web My Consumer, is allowed to issue credentials of type consumer credential, and that we trust those credentials from the time essentially for a year, maybe because it did buy access to our services. So we allow it to issue those credentials for the time, and we also allow the credential to include the claims, the claim role with the values reader. You can therefore differentiate at a very fine-grained level what you allow the different consumers. For example, by designing a paying customer is allowed to see some more details of the data set than non-paying customer. Okay. Then the verification usually did finish. When it's successful, our verifier will create a JWT token that contains the information from the credential. And this JWT token is then provided to the front end. Now, why do we use the JWT token here? This token will be signed not with a decentralized identity, but just with a key generated by the verifier. And the public key to this key is provided through a well-known JWKS endpoint. This is very similar to the way that other IDPs, or let's say traditional IDPs, do sign and create their JWT tokens. For example, if you do OIDC with Keycloak, you will also get a JWT token that you can verify at the well-known JWKS endpoint of Keycloak. This JWT token then can be used by the downstream components, and those components only have to verify the JWT token instead of the full credential. So we don't have to go the full round trip through all the lists, but just verifying the signature of the credential of the token, and then we can trust its contents. It also makes the integration with old OIDC-based services easier, because there are obviously a lot of services in the web already that understand JWT tokens very well, and they don't necessarily have to be rewritten to be part of a data space. And as the last step of our authentication, the JWT token is provided to the initiating application. Similar to we already know to the well-known OIDC flows, this token now can be used as an authorization header when actually requesting our data. In our FIWARE data space connector, this request will first hit our policy enforcement point, which has to do the authorization. We are using RP6 as a policy enforcement point. RP6 is an open source API gateway that uses a lot of additional API gateway features, provides a lot of additional API gateway features. But in our case, we're using it to actually verify the JWT token at our verifier endpoint, and then delegate the actual policy decision to our policy decision point. The policy decision point, in the case of our FIWARE data space connector, is the Open Policy Agent. Open Policy Agent is also an open source component, which is, I think, well known, which is used for policy evaluation, in this case, using the REGO language. The PEP provides the PDP information about the request, like essentially its metadata, authorization information, the request body, the headers, more or less everything that the PEP knows about the request, so that the PDP can do a proper evaluation of the policies. Now that the PDP receives the request, it starts to evaluate the request in the context of the configured policies. Therefore, it can retrieve additional information from a policy information point. For example, what's the current time, or we are planning to integrate some transfer protocols here, so that this information can be used as part of the policy decision making. And it also retrieves the actual policies to be evaluated. This also happens in reality asynchronously, but the PDP then has to retrieve the policies somewhat and will evaluate them. Again, we decided to use API6 and Open Policy Agent here because we have well established and maintained components that we can reuse instead of just rewriting new ones. Once all of this policy evaluation is done, the PDP will return its decision to the PEP. PEP can happily forward the request to the target service, and we will receive the response at our application. That's essentially a full walkthrough the identity and authorization in a flow in a FIWARE data space connector when a consumer tries to access a data provider. Now, obviously, we want to know how policies actually look like and how the authorization exactly happens. As mentioned, the authorization itself is handled by a couple of components. First one is the policy enforcement point. Second one, the policy decision point. We have policy information point, and we have a third one, which I did not mention yet, which is the policy administration point. This is a component code called ODRL PAP in our case, which is also maintained by the FIWARE community. And it allows us to define policies in ODRL, translates them into REGO, and provides them to OPA, so that to the Open Policy Agent, so that it can be enforced on the actual request. Because that sounds a little complicated what you just talked about, I will also go now into the details of our policy enforcement with ODRL here. And I will start with essentially what is ODRL. I think a lot of people already know this, but the Open Digital Rights language is a standardized policy expression language used to represent permissions, prohibitions, and obligations associated with digital content, enabling clear and enforceable rights management. Access to resources in a data space is essentially something essentially giving permission to access digital content based on policies, and as the description states, that already sounds very much like ODRL, which is one of the reasons we decided to use it, because we want to actually define policies on digital content. We again rely on a well-defined standard by W3C. We again have here the link to the ODRL model, and we use permissions as part of our policy framework to express the actual access right to this resource. One interesting feature that we have with our ODRL policies is that we can couple them with resources, like we do it, for example, or like it's planned to be done at DOME. I linked the DOME ODRL profile here. So let's say, for example, a service offering that is presented in the marketplace could be directly coupled with the policy that defines its access permission and can define where the service should be available, for example. Now, how does an ODRL policy look like? I decided to go for the JSON representation here again, because we already used a lot of JSON but ODRL is not necessarily restricted to JSON. The ODRL again has an add context that provides the JSON LD context for interpreting the policy structure, which is something that we now already know from verifiable credentials because they use more or less the same mechanism. A policy has an ID that uniquely identifies our policy, and it has a type. There are various types available in ODRL. In the FIWARE database connector, we currently only support ODRL policy. And then there comes the permission, which defines our actually access right rule. The example here is more or less, could be more or less read as DID web mydataprovider.org allows the web mydata consumer to read the resource URN NGSILD entity 1. So that would be a very basic policy that we could enforce on our resource. What does it mean in in practice? We get a request and we have to check the authorization that it's actually from that the request actually comes from this data consumer. We have to check that it's a read request, which in REST usually would be a GET, and that the target of our request is this actual entity. To do so, we translate our ODRL policy into Rego. That's where the ODRL PIP comes into play, which provides the CRUD API for creating the policy, which then translates those policies and stores them. The policies that we translated are then provided to the Open Policy agent through the so-called bundles API, which is something defined in OPA, and so that the Open Policy agent can use them to actually enforce it on the request. Now I'll have a look at how the translation to Rego actually is configured, because we don't have, let's say, a hard-coded mapping between the policies and the Rego code. We essentially have two central points in our ODRL PAP. There is a file called mapping.json, which connects the policy entries like the, let's say, ODRL read that we've seen before, with a predefined Rego script that our ODRL PAP uses. I can link to the mapping.json. I will not go through the details here, but it essentially defines which ODRL method, ODRL entry is connected to which Rego method. And then there is a second important folder in our ODRL PIP, which contains all the scripts that are already provided to the ODRL PIP and should be used for the translation. So the mapping.json tells us which entry connects to which part of the scripts in the Rego folder. This is again just a folder, so not too interesting. We have a number of Rego scripts here. You can go through this after the presentation if you want. All of this is extendable, so you can change the mappings inside the mappings.json or extend them on deployment. The same way as you could extend the Rego folder. So you can provide new scripts for functionality that you require for your specific use case. An example for this mapping would be, as mentioned, the action ODRL read. So I told you before that in our case, we usually map the ODRL read. So this was what I had in the example here. To read a resource, and in the REST world, a read usually is a GET. And we map this to a Rego method that is predefined. So our Rego method is called isRead. It's located in the ODRL action package, and it uses something something that we provide, which is helper methods. So we have some helper methods defined as part of our initial Rego scripts that provide commonly used information, like, for example, the HTTP headers, the request body, or the authorization information. For an isRead, we provide the HTTP headers, and the method will extract the isRead method will extract the request method and then check if it's a GET or not. Policy enforcement then is relatively easy because every of our policies can be condensed into a true or false decision. So what we have seen here, this is read. will in the end just give back a true or a false. All of those policies are then combined into a single main policy. And this main policy is what the Open Policy Agent actually evaluates. It will go through all of the individual policies in this main policies and just check if they are true or false. As soon as one of them evaluates to true, it will allow us the request, because then we have a policy that gives us permission to access the requested resource. If none of them evaluates to true, it will reject the request. I have a short view here how the main policy actually will look like. That's not very readable, because the IDs of the policies needs to be generated to match the Open Policy Agent format. That makes debugging a little complicated, but that's something that we work on, and hopefully debugging our policy system will become more easy in the future. Now, I also prepared a couple of examples on policies, because I think that makes it easier to understand what you can do with our policy system. All of those are not, so you cannot just copy this policy and use it, because for the sake of place or of room on a slide, I had to leave out some parts, but I have included the important ones. This, for example, doesn't have a context. If you know NGS-ILD, this would be very much understandable, but let's go through the policy itself. We again have a policy of type policy, and we define a permission. A permission has, again, as an assigner, so our data provider assigns this policy. And instead of our first example, we now define the target of our request. The target is not just a static resource anymore, but we can define constraints on this target. We do this by defining an asset collection, and then refining how this asset is allowed to look like. In NGS-ILD, you often have entities, and every entity has a type. And what we do here is essentially allowing access to all entities of a certain type. That's something we do with a plain constraint. We define a left operand, so this is more or less an equality if you would write it, which is taken from our Rego entry. We have here the namespace NGS-ILD, which is something that we already provide as a default in our ODRL PAP implementation, and the entity type. This will be evaluated by Rego and extract the entity type from our the requested entity type from our request, and it will check that it's an actually energy report. So requests are only allowed when the requested entity type is equal to energy report. Then we have, as an assignee here, another method that we already defined in our ODRL PAP. It uses the namespace VC here. We have it for verifiable credentials, and it essentially allows access to this asset for all authenticated users. So it just checks that there is an authorization header which contains a verifiable credential, and if so, we assume that is part of our data space, and everyone can read the energy report. And we again define down here our read action, which means every get to resource of type energy report would be allowed. Another example, we cannot just restrict access to certain targets or resources. We could also clearly define who is allowed to do so. So instead of putting refinement on the target, we would now do it on the assignee here. We now have type party collection, and we define refinement. We don't have, let's say, only single constraints. We could also support logical constraints. Therefore, the party that is trying to access our resource has to match multiple constraints. We use an AND here, which means every constraint inside this list has to be evaluated true. What we now do here is, again, using methods that we already defined in our ODRL PAP. The left operand here is now a VC role, which will extract the field role from our verifiable credential. This relies on a verifiable credential data format, which we sorry, which we ensure in the second constraint, but it takes out the role and it checks that operator is part of this list of roles inside this credential. This is something that the first constraint checked. Do we have the operator role as part of our credential? And the second constraint checks that our credential actually is of type operator credential. So it takes out the type of the verifiable credential, and it checks that in this list of credential types, operator credential is included. The right operand here is not defined as a map method that we have before, but just a value with a data type. So the operator role would be a string, similar as the type of our credential. And everything of that means the assignees are allowed to access if they have the role operator as part of their operator credential provided as the authorization header. We also can put constraints on the, I would say, general policy itself. So we have the target, the assignee, and the action relatively fixed here, but we only allow it for a certain time frame. So this constraint is, let's say, a logical constraint by default. All entries inside this constraint have to be true. And we're checking the date time here. So the policy says that the CRUD operation is only during a certain time frame. For example, because somebody wants access for this time. Which means left operand is, in this case, ODRL date time, which is evaluated to the current time, needs to be greater than this value. So it's only allowed after the 31st December 23. We see here the type is now not string, but date, which is important for the operator to do a proper comparison. And we also say that this date time has to be lower than 31st, 12, and 24. Again, date. And we now use not only the action read here, we also support the ODRL use here, which in our case evaluates to essentially do every REST request. So not only get, but also create, delete, or update. And as a last example, we are also able to use external information that is not directly available as part of the request, which could be seen as essentially a PIP integration. This is an example from the DOM marketplace. This is not yet in use there, but it's planned to be, which is a refinement on the target. So what we want to do here is a policy that only allows the owner of a certain resource, in this case of a product offering, to actually be able to update it. Therefore, we need to define our target, that our target has a certain owner field set, and that it is that it matches the owner that currently accesses the resource. Therefore, we have our left operand DOM op owner, and this would match to the following script in Rego, which first redirects the request that we get, or uses the requests that we get to actually retrieve the requested data, but not send it to our requester, but just take it and analyze and find the field in this entity that has the role owner, so that we can use the ID that is actually set in our target entity to compare it and only allow if this ID matches our current request. This ensures essentially that only people that are allowed to change, for example, product offering, can actually do that. Okay. Now that we're through with the ODRL examples, I'm essentially finished with my presentation. I think that was quite a lot. We will have a couple of minutes left for questions. I have the links to the slides again here. Slides are on my GitHub repository. I also provide some links that could be used as an entry point for further reading. Obviously, the FIWARE Database Connect repository. There's also a link to the code of the ODRL PAP and also to the now often mentioned DO Marketplace project. That's it for today. I think